Rust makes a very clear distinction between types that just hold plain old data versus types that hold a resource of some kind. And this distinction is an important part of how Rust prevents whole categories of bugs at compile time. In video 1, Why Rust is Safe, we introduced the idea of this distinction between copyable types and move-only types. We saw a struct called point with x and y coordinates that's copyable because it's just plain old data. And we saw another struct called file that contains a file descriptor representing a resource, the open file handle. We invented a keyword to make this a move-only type so it can't be copied, and that prevents use after close bugs. That was all made up syntax based on C. Now it's time to see how this stuff works for real in Rust. In video 2, Hello Rust, we covered the basic language syntax and the scalar types. All those types, integers, floats, bools, char, they're all just plain data, so values of those types can be copied freely. We're working our way through this map of the type system that I call the elements of Rust, which you can find at rustcurious.com. In this video, we'll cover the Rust syntax for tuples and structs, and we'll see how to make types that are move-only so they can protect resources by preventing copies. We'll also write methods that work on structs, and you'll see how to choose whether a method gets shared access to the struct or exclusive access or gets ownership of the struct. In Rust, if you have an instance of a struct, you know it's been fully initialized. If it owns a resource, you know it has exclusive responsibility for that resource. And you know that if you do something that would violate that exclusive ownership, you'll get a compiler error. The sense I'm trying to convey here is that working in Rust, objects just feel more solid. When you design the interface for a type, you get to specify how that type can be used, and the compiler has your back. The language gives you a lot of power to express what's allowed and what's not. Curious? We're doing tuples first because they're simpler, and then we'll get to structs. Here's a function that returns an integer, an i32. What if we actually have two different values that we want to return? Well, we could declare a struct type with a field for each of the values and return that. But sometimes we don't want to bother with all that, so instead we can just return a tuple. The return type here is the tuple of an i32 and a bool. A tuple is a lot like a struct, except you don't need a type declaration. You just write the fields separated by commas, put parens around it, and you've got yourself a tuple. So to be clear, i32, bool in parens is a type, and 0, true in parens is an expression that produces a value of that type. Now, when you call foo and you get back a tuple, how do you get at the individual fields? Well, a tuple is like a struct, except we don't name the type and we don't name the fields. So the compiler gives the fields names that look like integers. x.0 is the first field, the i32, and x.1 is the second field, the bool. Now, I want to be clear here. A tuple is not a list. It's not an array. You can't index into it. You can't iterate through it because the fields can be of different types. These field names look like integers, but they're just the names the compiler invented for the fields based on position in the tuple. It's perfectly fine to access fields of a tuple this way with dot notation, .0, .1, but it's often more convenient to destructure a tuple into its individual fields. So now we have a single let statement with a tuple pattern that creates the two variables a and b. A is assigned the integer and B is assigned the bool directly from the tuple. Now, when you're learning a new language, it can take a while to get familiar with which bit of grammar goes where, and this is a great opportunity to highlight that there are three different things here that all look like tuples. i32, bool is a tuple type. 0, true is a tuple expression. It constructs a value of that tuple type. And a, b is a tuple pattern that destructures a tuple value into its individual fields. There are three distinct pieces of grammar: types, expressions, and patterns. The language designers have made them look the same for consistency, but they're different things. This is a very simple example. Let's look at something a little more realistic so you get the idea of where tuples can be useful. This is a loop that iterates over the characters in a string. On any string, you can call the chars method to get an iterator over the individual characters. We're using that iterator with a for loop, so on each iteration the variable c is assigned with the next character and we can print it out. Now, what if I also want to print out an index that tells us which character we're up to? Well, on any iterator you can call the enumerate method. This is called an iterator adapter. It gives us a new iterator that returns a tuple containing the current iteration count along with the item from the original iterator. When we use that in a for loop, on each iteration the tuple is assigned to the pattern on the left of the in keyword. And it's convenient here that we can immediately destructure the tuple into separate variables. So now I is the iteration count and c is the character. Tuples are handy for making lightweight APIs like this that need to bundle a few values together. A tuple can have any number of fields. Here's a tuple with 3 fields. This is a silly example because I'm constructing a tuple with the expression on the right and then immediately destructuring it into separate variables with the pattern on the left. I'm just doing this to show you those 3 parts of the language: patterns, types, and expressions. And maybe this is obvious, but I want to point it out anyway. The expression is made up of simpler expressions. 0 is an expression, true is an expression, and the character h is an expression. By wrapping those together with commas and parens, we get a tuple expression that produces a tuple value. Similarly, i32 is a type, bool is a type, and char is a type, and we wrap those together to make a new tuple type. And A is a pattern, B is a pattern, and C is a pattern. Each of these binds a single variable to whatever appears in that position. And we wrap them together into a bigger tuple pattern to destructure the tuple value into its parts. The reason I'm going on about this is because I hope it helps you avoid some of the mistakes I see when people are new to the grammar. You can't mix type ascriptions into a pattern. The grammar for a let statement is let pattern, an optional colon with a type ascription, and an optional equals with an expression. The pattern and the type ascription are separate. Same deal with for loops. You might be tempted to write a type ascription like for I colon u32, but it doesn't go there. The grammar is just for pattern in expression. There are ways to ensure an expression gives you the type you want, and we'll talk more about that when we get to generics. Okay, back to tuples. A tuple can have a single field. This requires a trailing comma after the field to make it clear this is a tuple. Otherwise the grammar would be ambiguous. It might just be an integer wrapped in an extra set of parentheses. You don't see a tuple with only one field very often, but occasionally it's useful. A tuple can also have 0 fields. The empty tuple has a special name. It's called unit, and it has its own place in the elements of Rust. So here we have a pattern that matches unit with a type ascription of unit being assigned the expression unit. Yes, this line of code is completely pointless, but the unit type is quite useful. Unit is the type that represents nothing. When a function doesn't have a return type, it actually returns unit. So these two function declarations are equivalent. The unit type has one valid value, the empty tuple. Now, to store a value of a type that only has one possible value, how many bytes of memory do you need? Well, 0. There's nothing to store, so unit is a 0-sized type. We'll see more 0-sized types soon. Okay, so that's tuples. You take some fields, stick commas between them, wrap them in parens, and it's a tuple. They're convenient because you don't have to declare anything or write names for the type or the fields. You just use it wherever you need it. The downside with tuples is that often you really want to declare a type that conveys its own distinct meaning with its own name, its own methods, etc. So now it's time to talk about structs. I did that whole section on tuples first because tuples and structs are similar, and in terms of how they're represented in memory, they're basically the same thing. You have some fields, you glue them together in a fixed layout, and you call it a type. With structs, we have the same idea of packaging some fields together into a type, but structs add on all the other capabilities that come with declaring a distinct name for that type. Here's the Rust syntax for declaring our point struct with x and y coordinates. Inside the curly braces we have a comma-separated list of fields, and each field has a name and a type. The trailing comma after the last field is optional, but this is idiomatic style when you're writing one field on each line. It's a bit more consistent, and it means you don't have to edit that line if you add another field. To make an instance of a struct, you must provide a value for every field. There's no such thing as uninitialized memory or partial initialization unless you're in unsafe Rust. So we write the name of the struct, and inside the curly braces we name each field and give it a value after the colon. This is an expression that constructs a value of type point, which we assign to the variable p. Let's have a function that returns a point. The expression that constructs the point is the final expression in the function, so that's what gets returned. It's a matter of style whether you put all the fields on one line or on separate lines, and whether you include the trailing comma. And just to avoid confusion here, the outer point curly brace is the return type of the function, and the inner point curly brace is the start of the expression that constructs the return value. Once you have a struct, you can access its fields using dot notation as you'd expect. So we call origin, we get a point and assign it to p, and then we can access p.x and p.y. Of course, p is immutable by default, so if I try to assign to p.x, I get an error. We can declare p to be a mutable variable with let mut p, and now we can assign to the fields. You can't have some fields that are mutable and some that are immutable. The mutability of the whole struct is determined by the mutability of the variable that's holding it. This is called inherited mutability. The fields inherit their mutability from the variable holding the struct. If you want to make a struct with an interface where some fields are immutable, what you really want is private fields that are only accessed through methods. We'll get to that. So we've seen how to declare a struct, how to construct a struct, and how to access its fields. What about destructuring a struct? Well, just like with tuples, you can destructure the fields of a struct into separate variables. This pattern matches a point and creates two new variables, a and b. Field x is assigned to a and field y is assigned to b. So now we can print out a and b. Now, this might seem like a strange thing to do when we could just use p.x and p.y, but the fact that you can write a pattern that gets inside a struct is actually quite useful, especially when the struct is buried inside another type like an enum. What I want to highlight for now is, again, this consistency in the language across these three parts of the grammar: types, expressions, and patterns. A struct type declaration builds up a new type from the individual types of its fields. A struct expression builds up a value from the expressions for the values of its fields. And a struct pattern matches the whole struct and destructures it, so we can write patterns that access each of its fields. Now, in this example, I've chosen the variable names a and b to be distinct from the field names x and y. But if you're happy with variable names that are the same as the field names, then there's a shortcut for that. You don't have to say x:x, you can just say x, and you'll get a new variable with the value of the field x. So these two lines are equivalent. A struct pattern doesn't have to create a variable for every field. The underscore pattern matches anything and ignores whatever is there. So this pattern makes the variable x, but it ignores y. You have to acknowledge all the fields in the struct, even if you ignore their values. This pattern is a compile error because we didn't mention y. And this is useful because when you add a new field to a struct, you probably want the compiler to bring your attention to the places where you haven't yet thought about what to do with that field. However, if you have a struct with a lot of fields and you don't want to list them all out with underscores to explicitly ignore them, then you can use this ... syntax to say, ignore all the other fields. Okay, so with a struct, you choose a name for the type and you choose names for all the fields. With a tuple, you don't name the type and you don't name the fields. What would happen if a struct and a tuple got together and made a baby? Then you'd have a Tuple-struct. this is a struct where you choose a name for the type, but you don't name the fields. It's still a struct, but it's written with parens instead of curly braces, and the fields are just a comma-separated list without names. You can access the fields with p.0 and p.1, just like a tuple, but unlike a tuple, this is a distinct type with a name, and you can control the interface to that type. The most common use of tuple-structs is to create a new type that wraps a single field. When there's only one field, there's not much point giving it a name. The point of creating a new type is to protect against confusion with other types that have the same underlying representation. So kilograms and pounds might both be represented with an F64, but by wrapping them in distinct types, you can't accidentally use a value in pounds where kilograms are required. This practice is called the newtype pattern, and it goes way beyond representing quantities with different units. For example, a newtype might be used to protect a resource like a file descriptor or a memory allocation or an amount of money or permission to access an I/O port. We'll talk more about resources in a minute, I promise, but first there's one more kind of struct we need to see. You remember the empty tuple type, unit? Well, you can also have an empty struct with no fields. This is called a unit-like struct. So the struct foo is a zero-sized type. It has one possible value, which is constructed with the expression foo, and it can be destructured with a pattern that is just the name, foo. Okay, cool. Why on earth would anyone want to declare an empty struct? Well, when we get to generics and traits, we'll see how a library can provide an API that allows you to plug in values of your own type, as long as that type implements the right interface, the right trait. And sometimes you want to use that API with an empty object if you don't actually need to provide any data. So you can declare a unit-like struct, implement the right trait on it, and away you go. So now you've seen the three forms of structs: curly braces with named fields, parens around comma-separated fields without names, and a unit-like struct with no fields. Now let's write a function that takes a struct. The show function takes a parameter p of type point and prints out its coordinates. So we make a point and pass it to show, and this works. Now, what do you think happens if we call show again? This should work fine, right? It just prints out the coordinates again. Nope, this does not compile. Use of moved value p. Move occurs because p has type point, which does not implement the copy trait. When we called show the first time, the value of p was moved into the show function, and the variable p was marked as no longer available because its value is gone. So when we call show the second time and try to use p again, we get an error. What did we just learn? Our struct point is a move-only type. It cannot be copied. In Rust, when you declare a struct, it is move-only by default. It's being treated like a resource, something that should not be copied. Well, of course, a pair of coordinates representing a point is not a resource, it's just plain old data, so we'd like to make this type copyable. How should we do that? Well, I think the most natural syntax to make a type copyable would be to say hash square bracket derive parens copy comma clone close parens close square bracket. Nice, that's just intuitive, right? Okay, what the hell is this? All right, well, yes, this really is the typical Rust syntax to make a type copyable, so let's break it down. The hash with square brackets applies an attribute to the item that follows, in this case the type declaration. And the derive attribute says, hey compiler, give me the automatic implementation of some traits on this type. The copy trait is the one we want. It's the ability to implicitly make a copy when a value of this type is used by just making an exact copy of the bytes that represent the value, like with memcopy. And we also need the clone trait because the copy trait requires the clone trait. Clone is the ability to explicitly make a copy by calling a clone method, which is allowed to do arbitrary work to construct the new value. The easiest way to get the clone trait is just to derive it, so there it is. So now that we've made this struct copyable, we can pass it to the show function as many times as we want, and it will implicitly pass copies around just like a struct in C. As for the syntax, I know this looks awkward at first, but the design makes sense. We are adding on capabilities to the type. By default, the struct cannot be copied, but we can add on the capability to make copies. And you use this derive attribute to add lots of other capabilities too. So a realistic declaration of a point type would look like this. Each capability is defined by a trait that describes an interface with some required methods. This derive attribute is a very lightweight way to get an automatic implementation of some traits on a type. But it's also very common to implement traits by hand to customize the behavior. Traits are a really important part of the language. The trait system is very well designed, and I expect to make multiple videos on the topic. On the elements of Rust, the map of the type system, the top half is all the types built into the language, and the bottom half is all the traits built into the language. The compiler has special knowledge of the copy and clone traits, so here they are. Clone represents the ability to explicitly duplicate a value by calling a clone method, and copy represents the ability to implicitly duplicate a value by just copying the bytes under the hood. So, which types are copyable? All the scalar types are copyable. Arrays are copyable if the element type is copyable. And by the way, this language of saying a type is copy is common for talking about traits in the Rust community, but it feels weird to say out loud. Tuples are automatically copy if all the fields are copy. Structs and enums are not copyable by default, but they can explicitly opt in. Okay, so now that we have our point struct and it's copyable plain old data, let's give it some methods. In some languages, you'd write methods inside the curly braces of the type declaration, but not in Rust. Here we have an impl block which can implement methods on the type point. The impl block is separate from the type declaration, but it has to be in the same compilation unit, the same crate. So I've moved the show function into this impl block, and instead of taking a parameter p, it now takes the keyword self. The self parameter can only be used inside an impl block, and self is a value of the type named after the impl keyword. So inside the body of the show method, I can use self.x and self.y to print out the coordinates. The benefit of this special self parameter is that this method can be called using dot notation. So now I can call p.show. Whatever is to the left of the dot, in this case p, is passed as the self parameter. Methods can take other parameters too, but if you have a self parameter, it has to come first. You don't have to use dot notation to call methods. Methods are just regular functions, so you could instead go into the point namespace, call the show function, and pass p as an explicit parameter. That's equivalent to calling p.show. Calling with dot notation is really just syntax sugar. Right now, this self parameter is being passed by value. For a struct with lots of fields, you might not want to copy the whole object just to call a method. So let's change the show method to take self by reference. Now the first parameter is ampersand self, and this means we're passing a shared reference, which is a pointer to the struct. You remember the share keyword we invented in the very first video. This is a reference type that gives us immutable read-only access. Notice I didn't have to change the body of the method. I can still access self.x and self.y, even though the variable self is now a pointer type. With dot notation, the dereference is implicit, so you don't have to use an arrow operator like you would in C or C++. Similarly, when I call p.show, that works without any code change because the compiler will automatically take a reference to p when I'm calling a method through dot notation. But when we call show as a function and explicitly pass the self parameter, we now have to pass ampersand p, which takes a shared reference to the variable p. Otherwise, we get a type mismatch error. Let's add a method that updates the values in the fields. This offset method takes parameters dx and dy, which it adds onto x and y respectively. And so that it can update the fields, it takes ampersand mute self. That means self is a mutable reference to the struct. It's just like the borrow keyword we invented in the first video. It guarantees exclusive access to the struct. Some people refer to these as exclusive references. I tend to call them mutable references, but either way, the point is that you can only mutate if you have exclusive access. So let's call p.offset. Oops, but this doesn't compile yet. We get an error. Cannot borrow p as mutable as it is not declared as mutable. Calling the offset method implicitly takes a mutable reference, but right now p is declared as an immutable variable, so we can't do that. That's easily fixed. We just change it to let mut p. And now this works. We can call p.offset, which adds those values to the x and y coordinates, and the changes are visible when I call p.show. Functions inside the impl block are called associated functions because they are associated with the type. They are in the namespace of the type and they can take a self parameter, but they don't have to. The origin function doesn't take any parameters, but it constructs a point value, so we could move it inside the impl block, and that way it's in the namespace of point. This pattern of having factory functions that construct values is very common in Rust, and it's a lot simpler than the story around constructors and initialization in C++. So we can write associated functions that don't take self, or that take self by value, by shared reference, or by mutable reference. This gives you a lot of control over how a type can be accessed when you're designing its interface. Of course, to really control what a type can do, you need private fields that can only be accessed by the interface you provide. In a program of any complexity, there are many moving parts, and it's a lot to keep track of. The fundamental tool we use to cope with this is the separation of concerns, divide and conquer. We try to make clean boundaries between different parts of a program with reusable modules that we can think about one at a time. In the code I've shown you so far, we've been doing everything inside a single module, the root module. To demonstrate private fields in structs, we need another module because privacy is enforced at module boundaries. Our point type deals with two-dimensional Cartesian space, so let's make a module called Cartesian. There are two ways to make a module, and both use the mod keyword with the module's name. The first way is to write the body of the module inline like this, inside curly braces. The other way is to just declare the module and put the code in a separate file. So if we say mod Cartesian in the root module, the compiler will look for the file cartesian.rs or cartesian/mod.rs. Modules can be nested, so you end up with a directory hierarchy that matches the module tree. So let's move the point type declaration and the impl block into cartesian.rs, and we'll keep our main function in main.rs. This is main.rs. We declare the module Cartesian, and for convenience I'm going to import the type name point into the current namespace with the use declaration. I'll use that when I call point : origin. This doesn't compile yet because the Cartesian module currently doesn't make anything public. It's all private by default. We're going to need access to the point type and the functions origin, offset, and show. So in the module, I add the pub keyword to the type declaration and the functions I want to export. And now this compiles. If I had other functions here that should stay private, I'd just leave out the pub keyword and main would not be able to access them. Private items are only visible to the module where they're declared and any submodules inside that module. Even though I've made the struct type public, the fields of the struct are still private. For a lot of types, that's exactly what you want. Private fields that can only be accessed through the methods you make public. So right now, if I try to access p.x, I get field x of struct point is private. What's more, I can create a point by calling origin, but I can't construct one directly. To use the constructor syntax, I have to name each field and give it a value. But if I try that here, I get the same error. Fields x and y of struct point are private. So the module is in complete control of the private field values. For this point type, it actually makes sense for X and Y to be public because this is just a plain old data type. So let's do that. The pub keyword goes right before each field name. And now other modules can directly construct instances and read and write the fields. Okay, here's a fun question. What's the difference between these two declarations of a struct called token? The first one is a unit-like struct with no fields. The second one is a tuple-struct with one field of type unit. These are both zero-sized types. Are they equivalent? No, they're different. The first one has no fields, so anyone can construct a value of this type just by naming the type. The second one has a private field, which means other modules cannot construct it. Here's an API for a ride, where you purchase a token and then redeem it to use the ride. This is all inside a module called ride, which I've written inline this time, but it could equally be in a separate file. So we have a purchase function that prints enjoy your ride and then returns a token. And the token has a method called redeem that takes self by value and prints out whee! Cool, so let's take it for a ride. In main we call purchase, we get back a token, and then we call token.redeem. Great, this works. Now let's see if we can cheat and get some free rides. Can I redeem the same token twice? No. If I call token.redeem again, I get the error use of moved value. The move occurs because token has type token, which does not implement the copy trait. It points at the first redeem call and says token was moved due to this method call. Then it points at the second redeem call and says value used here after move. And finally, it points at the declaration of the redeem method and tells us, note, token redeem takes ownership of the receiver self, which moves token. See, error messages are actually cool. This told us exactly what happened. The first time we called redeem, the token was consumed, so we no longer have it. It disappeared into the self parameter of the redeem method. What if I try copying the token? Error, use of moved value token 1. It's a very similar error, but this time the move happens when I assign it to token 2. The assignment is a move, not a copy, so token 1 is invalidated and I can't call redeem on it. And what if I try making my own token? Error, cannot initialize a tuple-struct which contains private fields. So in code that's outside the ride module, the only way to get a token is through the public purchase method. So even though it's a zero-sized type, it doesn't contain any data. We've built a type that represents a resource. If you have a token, it means you've purchased a ride and you haven't redeemed it yet. And of course, we could store whatever fields we want in the struct to keep track of the resource. This pattern is everywhere in Rust. All the collection types track their heap allocations as resources. File objects track their file descriptors. Embedded firmware can track that there is only one user of some hardware resource. You get the idea. There's one more thing needed to make all those use cases work well, and that's to take care of cleaning up the resource when the object goes out of scope. For that, we need destructors, which in Rust are controlled by the drop trait. And oh look, here it is, right next to the copy and clone traits. Destructors are actually quite a deep topic in Rust. There are some interesting cases for the language to handle when a variable might be valid or might not, depending on which branch was taken, leading to something called drop flags. Destructors can have some interesting interactions with thread unwinding if there's a panic. And you can't always rely on destructors running. It is possible to leak objects if you try hard enough. So destruction is a topic for a whole other video. We're getting to the end of this one, but I need to show you one last thing before we wrap it up with a practice exercise. What if you have a struct that holds a resource, like a string, and you want to let your clients access that resource without giving up ownership of it? This is the dynamic string type provided by the standard library. It's a struct and it has private fields because it manages a resource, the heap allocation containing the bytes of the string. The bytes are on the heap because the length of the string can change at runtime. So the struct contains a pointer, and it has a destructor that frees the heap allocation when the string is destroyed. String is not copyable, it is a move-only type because it owns a resource. If we did allow the string struct to be copied, that would just make a copy of the pointer. So then there would be two structs pointing to the same allocation on the heap. That would be bad because when one struct frees or reallocates the string, the other struct would be left with a stale pointer, leading to a use after free. So I'm using string as an example of a type that holds a resource, and now I want to make a struct that holds a string in a field. This struct, video, has a private field called title that holds a string, and because string cannot be copied, that means video also cannot be copied. If I tried to implement the copy trait for video, I'd get an error. The title field is private, so to make a video we have a factory function called new that takes a string and returns a video with that string in the title field. And notice I'm using another little shortcut here. The field name is title and the variable from the parameter has the same name. So I don't have to say title : title to name the field and give it a value. I can just say title because the local variable has the same name as the field I'm initializing. Next, I want to provide read-only access to the field with a method called title. The title method takes self by shared reference, &self. That's the right choice because I want the client to be able to read the title whether they own the video object or they have exclusive access to it, or even if they only have a shared reference to it. Choosing &self here gives my clients the most flexibility. So what type should this method return? What do I give the caller when they want to see the title? Well, let's try returning a string. So I say the return type is string, and in the method body I return self.title. This does not compile. Error cannot move out of self.title, which is behind a shared reference. The move occurs because self.title has type string, which does not implement the copy trait. So the compiler sees that we're trying to return self.title by value, which would mean moving it out of the video struct. And we can't do that because, well, first of all, we can't mutate the video because we're accessing it through a shared reference, which is read-only. But even if we take self by mutable reference with &mute self, we get the same error. We can't just rip the title string out of the video because the video object still has to be valid after this method returns. This method is just borrowing access to the video struct. In both cases, the error message goes on to make a suggestion. Consider cloning the value if the performance cost is acceptable, and it shows us the syntax for doing that. So the string type doesn't implement copy, but it does implement the clone trait. That's the one where you call a clone method that can do arbitrary work to come up with a new instance. In the case of a string, this is a deep copy. When we call self.title.clone, it makes a new heap allocation and copies all the bytes to make the new string that we return. I want to pause here to note types that implement the clone trait are an interesting halfway point between plain old data types that can be copied, like scalars or the point struct, and resource types that can't be copied. String implements clone. It's a resource type in the sense that it manages a heap allocation, so you can't just copy the bytes of the string struct because then the copies would be fighting over the same heap allocation. But it's kind of a plain old data type. It's just a string, and you can make a copy by cloning it if you need to. Anyway, in this particular case, cloning the title works, it compiles, but I don't feel great about it. All I want to do is give the caller read-only access to the string. Surely we don't have to duplicate the whole string just for that. Instead of cloning the string and returning it by value, we can return a shared reference to the one we already have. So I change the return type to &string, and in the method body I say &self.title. This is much better. This is super lightweight. We're just returning a pointer to the field. And it's safe because at each place where this method is called, the compiler tracks the returned pointer. For as long as the caller holds the pointer to the string, the compiler treats the video as being in a shared read-only state. So while it's shared, nobody can mess with the video object or the title string in any way that would invalidate the pointer. This is cool, but actually we're not done yet. This particular string type is one of several options for managing a UTF-8 string with different trade-offs. For example, there's a copy-on-write string type. Maybe one day I'd like to change the private field to use a different type to store the string, but right now that would be a breaking change in the API. I'm exposing to my clients the fact that I'm using this particular string type. There is a better option. I can change the return type to &str, all lowercase. This is a shared reference to a string slice, which means it points directly to the UTF-8 bytes of the string in the heap allocation. I don't even have to change the body of the method because the string type has the ability to automatically coerce the type. If you have a reference to a string struct, you can implicitly turn that into a reference to a string slice, str. This is better because across all the options I might choose to store the title string, they can all expose their underlying UTF-8 storage as a string slice. So the client no longer knows or cares which particular string type I'm using. Separation of concerns is a beautiful thing. Anyway, there's more to say about all that, and I'm planning a video going into detail on strings, but now the point is that you've seen how a struct can safely provide public access to private fields. Okay, finally it's time to wrap this up with some coding practice. It won't take long to explain the exercise because it uses the code I've just shown you. To get the playground with the exercise code, just go to rustcurious.com/4, scroll down a bit and, oh, hang on, what's this? Boost your learning. For purchase, Lesson 5, Destruction. With no garbage collector, Rust relies on deterministic destructors to manage the life cycle of objects. Write types that safely encapsulate raw resources, reason confidently about the scopes of locks, and understand the limitations of Rust's guarantees around resource leakage. That's a coincidence. We were talking about destructors just a minute ago. Cool, well, I'm definitely bookmarking that one. Anyway, on with the exercise. Most of this is exactly the code for the video type that we just saw. At the top is a comment explaining that your job is to add some fields to track the number of likes and dislikes on the video and add methods so the test passes. The test expects to call some methods that don't exist yet. Add like will increment the number of likes, add dislike will increment the number of dislikes. The likes-dislikes method will return a tuple containing the number of likes and the number of dislikes. And the like ratio method will return the number of likes divided by the total number of likes and dislikes. At the bottom of the file is the unit test. You don't need to change anything here, but reading it helps clarify what to do. The add-like method is called 3 times, and add-dislike is called once, so the likes-dislikes method should return a tuple with those counts. You can choose your integer type. The like ratio method is expected to return a floating point value, so you can choose F32 or F64. There's nothing too fancy happening here. This is just to get some practice writing struct fields and methods that access them. Methods that mutate fields should take self as a mutable reference, and methods that only read fields should take self as a shared reference. You don't need to do anything with destructors in this exercise, but I will walk through a solution at the start of the video on destruction. Okay, that's it. We made it. I hope what you get from all this is a sense that Rust provides a very rigorous basis for designing types that handle resources. The type system is explicit about what can be copied or cloned. There are clear boundaries around access to private fields, and you can safely expose references to internal fields. You can control how objects are created, and when an object is consumed, there's no chance of it being accidentally duplicated. This means we can design interfaces like the token API that provides some useful guarantees at compile time. We are making our way through the Rust type system. The next free video will be about enums, which form an absolutely crucial part of the language. If you haven't yet worked in a language with this kind of support for tagged unions, I reckon after this one you'll be wondering how you ever managed without them. So stay tuned, stay curious, and I'll see you soon.